the manner in which atoms are held together, but this affects both chemical and physical properties. An understanding of chemical bonding leads to an understanding of both natural and man-made materials and how we can manipulate them. We'll start off by looking at the types of chemical bonds. Then we'll introduce the idea of electronegativity, and then relate this to bond polarity and dipole moments within molecules. Now, questions to consider as we're going through this material is, what is meant by the term chemical bond? Think about why atoms bond with each other to form compounds, and think about how atoms bond with each other. Now, bonds are simply the forces that hold atoms together, and we can examine them through measuring bond energies, where bond energies are simply the energy required to break bonds. Now, a chemical bond doesn't have a simple, complete definition. Again, chemical bonds are the forces that hold groups of atoms together and make them function as a unit. A bond will form if the energy of the aggregate is lower than that of separated atoms. We've seen ionic bonding in several examples where we have full transfers of electrons to form ions. In ionic bonds, we have something that easily loses electrons like a metal, and something that easily accepts electrons like a nonmetal, which combine. We can use Coulomb's law to calculate the energy of the interaction between a pair of ions, where the energy is equal to 2.31 times 10 to the minus 19 joules nanometers times Q1, Q2 over R, where Q1 and Q2 are numerical ion charges and R is the distance between ion centers in nanometers. The bond length here is the distance R, where the energy is minimal. When we look at the interaction of two hydrogen atoms, we no longer have that formation of ions. When we have two of the same atoms bonded together, there is some interatomic distance where the energy of the aggregate sharing electrons between those two centers of positive charge is minimum. Keep in mind that the hydrogen atom has a proton in its nucleus and one electron, again at some distance R, which is the bond length, 0.074 nanometers. The attractive forces of the positive and negative are optimal such that electrons reside between the two nuclei. If the atoms get too close, repulsions become too great. If they get too far apart, they lose the stabilization of the plus-minus interaction when electrons are shared equally between the identical atoms. When we have this equal sharing of electrons, we have a purely covalent bond. So some of the key ideas in bonding that we've already explored are the idea of the ionic bond, where we have a full transfer of electrons, the covalent bond, where electrons are shared equally by nuclei. But what about the intermediate cases, where we have two nonmetals, which are close in their ability to share electrons, but don't fully transfer or share electrons equally? In this case, we have a polar covalent bond, where we have this unequal sharing of electrons between atoms in a molecule. This results in a charge separation in the bond, where we have a partial positive and partial negative charge in our molecule. If we look at hydrogen fluoride, where hydrogen is represented by the blue sphere and fluorine is represented by the green sphere, we have this unequal sharing of electrons, and so there is a partial positive and partial minus or negative end to our hydrogen fluoride molecule. The delta plus represents the partial positive end. The delta minus represents the partial negative end. If we put this molecule into an external field, then the molecules will orient themselves with the partially positive end toward the negative pole and the partially negative end toward the positive pole. In the absence of an external electric field, the molecules are random, as is shown in A. Now this partially positive and partially negative end to our molecule implies that there is an unequal sharing of electrons. And so this brings about the idea of electronegativity and differences in electronegativity. Electronegativity is the ability of an atom in a molecule to attract shared electrons to itself. For a generic molecule, HX, the relative electronegativities of the hydrogen and X atoms are determined by comparing the measured HX bond energy with the expected HX bond energy. On the periodic table, electronegativity generally increases across a period and decreases down a group. The range of electronegativity values is from 4 for fluorine, the most electronegative atom, to 0.7 for cesium, the least electronegative atom. Electronegativity increases in the direction of fluorine. Electronegativity values were established by Linus Pauling, who won a Nobel Prize in both chemistry and also in the Nobel Peace Prize. He determined these differences between expected and actual bond energies and tabulated them on the periodic table. So we can see here that electronegativity increases in the direction of fluorine. These differences in electronegativity result in differences in bond types. When we have zero difference in electronegativity, because we have the same element bonded together, we have a purely covalent bond type. When we have very large electronegativity differences, as is seen when we have a metal and a nonmetal, we have ionic bonds. When we have intermediate electronegativity differences, this is where we get our polar covalent bond type, where we have an uneven sharing but not a full transfer of electrons. Notice that as ionic character increases, covalent character decreases in bond type and vice versa. If we look at a series of bonded species, usually we say that between 0 and 0.4 electronegativity difference, we have covalent bonds. Between 0.4 and 1.9, we have polar covalent bonds, and above 1.9 electronegativity difference, we have ionic bonds. Now if we take our HF molecule, our hydrogen fluoride, and make an electrostatic potential map showing areas of high electron density in red and areas of low electron density in blue to violet, then we can see the partially negative end of fluorine, of hydrogen fluoride, is on the fluorine, shown in red, and the partially positive end of hydrogen fluoride on hydrogen is shown in purple. Because of this electronegativity difference, we have a lot of electron density built up on one side of our molecule and very little electron density on the other, which creates a dipole moment where we have one pole of negative charge and one pole of positive charge. A dipole moment is a property of a molecule whose charge distribution can be represented by a center of positive charge and a center of negative charge. We typically use an arrow to represent a dipole moment, and we point to the negative charge center with the tail of the arrow indicating the positive center of charge. If we look at the water molecule, the oxygen of water is more electronegative than hydrogen, so we have a partially negative oxygen and partially positive hydrogens. This gives us a dipole moment, as is shown in B, in the direction of oxygen. We could also look at an electrostatic potential map for water and see the area of red around the oxygen and the blue area around the hydrogen, indicating area of high electron density on oxygen and area of low electron density on hydrogen. The ammonia molecule has a lone pair of electrons on nitrogen. We have a high electron density on nitrogen, as is shown by the delta minus. We have areas of low electron density on hydrogen, as is shown by the delta plus. If we draw a dipole moment, as is shown in B, the dipole would be in the direction of nitrogen because the positive end is by hydrogen, the negative end is on nitrogen, and our electrostatic potential map in C shows the same sort of distribution of electron density. High electron density around our nitrogen, low electron density around the side of the molecule where the hydrogens are. The carbon dioxide molecule has this partially positive carbon and partially negative oxygens due to electronegativity differences. This gives us a dipole moment in the direction of oxygen from our carbon. Because this is a linear molecule, the dipole moments are in opposite directions with equal magnitude and will cancel each other out to give our molecule no net dipole moment. We can see from the electrostatic potential map that there are areas of very high electron density centered at the terminal oxygens, and the center of the molecule where our carbon is an area of very low electron density. Whenever we have a symmetric linear molecule, such as carbon dioxide, we will have a cancellation of polar bonds to give us no net dipole moment. There are other molecular geometries that we will see as we go through this chapter in which we can also have cancellation of dipole moments to give no net dipole in the molecule. When we have planar molecules with three identical bonds at 120 degrees, known as a trigonal planar molecule, we can end up with cancellation of dipole moments for no net dipole on the molecule. When we have a tetrahedral molecule with four identical bonds at 109.5 degrees and a symmetric molecule, we can have cancellation of our dipole moments to end up with no net dipole.